and let me know if it switches off. Okay. Okay guys, so yesterday we were discussing shear center, and so in this chapter we started off with shear, importance of shear. That's what we focused on. After that, we have to understand the flow of shear within a cross section, and then these are sort of tools which are necessary to understand the concept of shear center. Okay, so the flow of shear within the cross section and within the in transverse and longitudinal directions, that's important for shear center comprehension. So what we have is, now I'll discuss shear flow, how the shear flow takes place within a cross section, and essentially within a longitudinal section of a structural component, and then from there onwards I give you a concept of shear center. How does shear center comes into play? So if we have a load applied, so imagine we have a section which is cantilevered of a support, okay, and we apply load P on it. Okay, so what will happen is that we will have a bending moment diagram. That diagram will show that towards the load we will have a smaller moment, and as we make our move towards the support we will develop bigger moment. Okay, and as you can see that it starts from 0 and keeps on reaching to a maximum magnitude. So assume we take a section, any section. So we take section 1, 1 and 2, 2. Now these two sections, they are at a finite distance apart, or imagine, let's for argument's sake say that they are at a differential distance from each other. Now since we have a change in moment, that tells us that there is going to be a shear. It's always the change in moment which gives rise to shear. So because we have got change of moment, we will have shear in the section. Now the moment at section 1, 1 is smaller than moment at section 2, 2. So that means overall the structure is in equilibrium. Okay, the structure is not moving. So that tells us that there can be an imbalance in the shear force, in the horizontal force between section 1, 1 and section 2, 2. But that imbalance is compensated by the shear force. Okay, so imagine if we take a section out of So we have taken a section out of this beam. This is the 3D, okay? So 3D image of this section, but we have got this small section, and we will have a Okay, so we have a section taken from this member, and in this section we have got a moment which looks like this. So remembering that this is cantilever beam, so the top flange will be in tension, which is shown over here, and the bottom flange will be in compression. So this is our section 1-1, and this is our section 2-2. Okay, so now because this moment is smaller than this one, okay, this moment is smaller than this one, so that means that there is an imbalance. Okay, this is bigger force and this is a smaller force. So we have to apply a bigger force in this direction, in order to compensate for this bigger force. And that I have applied over here as something like this. Okay, so this is that force which I have, which is the difference in the tension force. Okay, and similarly at the bottom we have got compression, and this compression is bigger. This one, section 1-1 compression, is smaller than this one. So we have to apply a force in this direction in order to compensate for this force, and that I have applied over here in this direction. Okay, is that clear? So these two, so from there, so this is the 3D image of this section, and imagining that this is an I section, we assume that this I section is discretized into small boxes, and we take one box, and in this box we say that this is the compensatory shear force in this direction, and at the lower flange there is a compensatory force which is facing out. This face, so this is our 1-1, and this is our section 2. Okay, so that's what we have now. Because the section is in equilibrium, so therefore equilibrium condition states that all the forces and moments must be equal to 0, and this box must be in equilibrium. So the forces must be 0. So we have, if this is, we will have to apply an equal and opposite force in this direction. This is causing counterclockwise moment. We will have a clockwise moment in this direction. And similarly, this one is, we apply opposite force in this direction, clockwise, and anti-clockwise is in this direction. So in other words, we are saying that there will be a shear flow which will start its way like this. We can apply the same principle over here. So we will have a shear force which starts moving in this direction. Then this shear force will make its way up. It will start moving in this direction, and from there onwards this will start moving like this. Okay, that's what will happen. If we have forces in this direction, we have got force in this direction, so obviously this is starting from here, going up, and then going like this. So this is actually the shear flow within the cross section, and we know that horizontal shear has got an equal vertical shear. Okay, or in other words, this transverse shear, these shears will have equal longitudinal shear. So you will have a longitudinal shear corresponding to this in this direction. Okay, so I mean that goes without saying. Okay, so you will have a longitudinal shears also developing over here. Now let us apply the same principle over here. So in this case, you will have again a box. I am taking the same thing. So this essentially is a piece of taken off from this flange. So the shear flow will be okay, that's the shear flow in this channel section. Now, let us say that the load is applied over here. Now, once we have established our shear flow, after this we will check whether equilibrium on a global scale is satisfied. On a global scale, I mean overall in this structure, this component should be in equilibrium. So, if this is our x-axis, y-y and z-z axis, so summation of all the forces, the equilibrium conditions are the summation of all the forces in x must be equal to 0, the force in y must be equal to 0, these are the 6 equilibrium conditions and they must be satisfied. Now, summation of forces in the x direction must be equal to 0, so we assume there is no load applied in the x direction, so this will be automatically satisfied. Summation of all the forces in the y direction must be equal to 0, so we have got the force P applied in this direction, imagine, okay? So, we have got a force P applied in this direction and this is taken by the force in the web. Okay, so please note this, that you have got force P applied over here and this force is mainly resisted by the web. The flange has got a very small shear which is taken. You can see that this force P is mainly taken by the web. Okay, so the web takes maximum of your applied shear force. So shear force at y is equal to 0. Okay, so this all, if you add them up, you should get load P. Okay, so this should add up to load P. And summation of forces in the z direction must be equal to 0. So by default, we are assuming that there is no pre-stress or any force applied in the z direction. So that is 0 by default. Then summation of moment about x equal to 0. So this gives you the Bernoulli equation, which is stress is equal to my over r. So it's this one, and we did it previously, how that is derived from summation of moment about x equal to 0. Okay, so that is actually your Bernoulli equation. Then we have summation of moment about y must be equal to 0. So about y, if the load is applied exactly in line with this y-axis, so there is no force, there is no load or no moment applied in the y direction. So by default, moment about y is 0. Just think, about y you don't have any lever arm. Okay, if this load you apply over here, you will develop moment about y-axis. How can you develop moment about y-axis? If you have a load applied in this direction, in the z direction, and you take, so that will, no, if you have x direction, yes, you can have x, no, but you can have load in the z direction, and then about y, it can give you moment. Okay, if you apply load in this direction, for example, so about y it can give you moment. If you apply load in the x direction, in this direction, okay, so that will give you moment. That can also give you moment in the y direction if that is applied off the center. Okay, so it is all the moment, all those forces which cause the moment about y axis, but that is not there. Then we have summation of moment, so that is 0. Summation of moment about z must be equal to 0. Okay, so about z you have this shear flow and this shear flow. They are causing one moment. Okay, this one is causing one moment and this one is causing one moment. Isn't it? Look at this one. This will have a resultant force and this will have a resultant force. These both cause couple, okay, and that couple moment is resisted by the couple moment in this direction. So that is satisfied. Agreed? Yes? So this couple's summation of moment about z-axis is satisfied. This is due to the fact that I section is symmetrical in both the directions. But if you don't have symmetry in any of the direction, if you have symmetry only in one direction, then this won't be satisfied. As you can see in this channel section. In channel section again you have this moment which is in this direction and in that direction, and that is causing moment about z-axis, which is this one. Okay, so this is causing a moment about z-axis, but there is no material to resist that moment as you had in this case. Okay, so this will twist. So in order to avoid this twisting, what you have to do is you shouldn't apply the load exactly at y. You should put it at some distance from y. Okay, so from this y plane, you should put it at some distance, and that distance can be E in such a way that P times E is equal to the moment which is caused by this one. Do you understand my point? So if you don't apply the load at E distance from this y plane, then what will happen? Your section will twist. So please notice that in the case of this symmetrical section, in the case of those sections which are unsymmetrical in one direction, you have this problem of twisting, and that is avoided by applying a load at a distance at an offset from the plane, y plane. Okay, and that is what. So this E is called shear center. Shear center comes into play where you have no axis of symmetry in any direction. Where you have a section which is symmetrical in one direction and unsymmetrical in another direction. Okay, so I repeat that shear center only is applicable in those cross sections which have symmetry in one direction and non-symmetry in the other direction or other orthogonal direction. So see, this is symmetrical in the x, about the x plane it's symmetrical, but about the y plane it's not. So therefore this is a candidate for shear center. Now this one is symmetrical in both directions, so you don't have any problem of shear center, and you can very easily put the load along the y-axis. If you have unsymmetry in both the direction, then you have unsymmetrical bending. Okay, so it will again twist, but that is because of unsymmetrical bending. Okay, so the main idea is to apply the load in such a way that you avoid twisting. So if you have a same cantilever section made of a channel section, okay, and you are asked to apply the load at the tip of the cantilever, okay, so you won't apply it on the y-axis, on the symmetrical axis. You have to apply it at a distance, at a shear center from the y-axis, in order to avoid unsymmetry, in order to avoid twisting. If this was an unsymmetrical section in both the planes, okay, like a Z section, like an angle section, then you would have an issue of unsymmetrical bending. So in that case, you would be required to apply the load along what is called principal plane. So in the shear center problems and in the unsymmetrical bending problems, the whole art is to apply load in such a way that the twisting is avoided. You understand my point? So that is an important factor. So if you have similarly a C section, please remember that we are dealing only with thin wall structure. The reason I am making this a bit thicker is just to show you the shear flow. Okay, so we are dealing with a thin section with not a very thick section. In other words, the thickness of the section is of very small order of magnitude as compared to the width and the depth of the section. Okay, so that is an important thing to know. So in this case, you have got shear flow in this direction. This is also. How would you have a shear flow if I use it? If I use it as a cantilever, what do you think? In this channel section, how should I draw my shear flow? So again, the same thing. Okay, it's the same thing as. But this will be in the radial direction. And so this will again be a radial direction, and you will have to apply load in some particular shear center, at a particular shear center from the non-symmetrical axis. Okay, so that is. Okay, so what will happen if we have a cross section like this one? I want to use this one as a shear center. Now in this case, as I told you, the load is applied in this direction. So in other words, the load has to be somewhere. The load is like this. Okay? This flag, if this you call or this leg, okay, leg in this direction, that is not taking any shear. Remember I told you that you need a vertical member like this in order to take your shear. The percentage of shear taken by this member, okay, is very small. So similarly, the percentage of shear taken by this guy will be very small. So what will happen is that you will apply the load over here and your shear flow will be simply like this. This won't contribute. Okay? So in other words, you can see, you can develop your concept that you need a full body in order to have a finite shear flowing through it. Okay? If that body is lying like this and you are applying a load like this, that is not going to take your applied load. So in other words, if I have got this load applied, okay, and I want to transfer it via some component, and you are thinking that how should you place your component? Should it be placed like this or like that? Or like this? So the concept of shear flow tells us that if I place it like this, this shear, there will be a minimum shear taken by this, and this can fail. If it is placed like this, it can take some shear, but still the best way to place this component is like this, because your shear is going like this and you will have significant material available for your shear flow. You understand my point? So the best is like this. If you are applying the load like this, you should have enough material which is able to resist it. Okay? So you know, like if someone is fighting karate or something, so you know they always keep their chop like this, isn't it? Because this gives a significant shear, transfer a significant shear. This one is not a significant shear, it's just a slab. But if you want to give a proper damage, okay, so you make it like this. Yeah, so that will transfer, that will hurt a lot, okay, and bring damage. And similarly, when you make a punch, so look, this is a significant force and this gives more damage as compared to slap. So therefore you give a slap to children and you give a punch to elders, isn't it? Yeah, that's right. Okay, so that is your shear center, and